Hello there. Today we will be covering the intro to chapter 6 on exponent rules, as well as simplifying radicals, which is a review from last semester. So to start out, we have exponent rules when we have a negative exponent. First of all, we'll recall that exponents are the little numbers up top, like this 5. So if we have a negative exponent, for example, say a to the negative x, this is really going to be simplified as 1 over a to the x. I like to say if there's a negative exponent, he is unhappy having this whole term in the numerator. He actually wants to be in the denominator and will be happy that way. So you flip him down, and then he becomes 1 over a to the x, happy. Okay, so an example of this with numbers is, say, 7 to the negative second power. This is equivalent to 1 over 7 to the second power. He was unhappy in the numerator, so he goes to the denominator. Then you do 7 to the second power, which is just 7 times 7, or 49. So 1 over 49. All three of these are actually equivalent if you tried to find a decimal form of them. All right, and then a second example here, say we have 1 over x to the negative fourth. You can go from the denominator to the numerator if the denominator has an unhappy exponent. He's not at home, he'd rather be in the numerator, so you have x to the fourth over 1, which is really just saying the same as x to the fourth. Now, possibly the most simple exponent rule is the fact that if anything has the exponent of 0, that equals 1. So say you had 5 to the 0 power, that equals 1. If you have parenthesis a negative x to the 0 power, that also equals 1. So anything to the 0 power is equal to 1. Multiplication of like-based exponents really just means that you add them. So you keep one of the bases and then you add the exponents. So for example, we have x cubed times x to the fourth. Notice the bases are both x's. You simply add your exponents and you get x to the 7th. If you have power to a power, you have only one base. And then you have an exponent on the outside of parentheses. This is just saying that you are going to multiply your exponents this time. So for example, we have x cubed all to the fourth power. This is equal to x times 4, which is equal to x to the 12th power. Then we have product to a power. We have two different bases inside of a parenthesis with an exponent on the outside. This is sort of like a distribution of an exponent where we take this x to each term on the inside of the parenthesis. So we have a to the x times b to the x. So for example, if we have 2 and x, two different bases, all squared, or sorry, let's say cubed. All cubed, we distribute that cubed exponent in. So we have 2 cubed times x cubed. So 2 times 2 times 2 is 8, x cubed. Okay? And then we have division of an exponent. Notice, like bases, they're both a's. Similar to multiplication, when we added, we are going to simply subtract our exponents. Notice the numerator minus the denominator is how we do it. So a minus x, sorry, a to the x minus y is what we have. So for example, we have x cubed over x squared. This is the same thing as simply subtracting our exponents, numerator minus denominator, so x to the first power which is really just the same as x. And then quotient to a power is similar to power to a product to a power. So we have two different bases, a divided by b to the x power. This is the same as a to the x over b to the x. It needs to go to both numerator and denominator. So for example, we have 3 over x squared. The squared just goes into both terms. So we get 9x squared. Now we're going to practice with these. There actually are quite a few different ways that you can go about these. So you might have said, oh, I saw this a different way. You will get the same answer as long as you do it correctly, okay? So what I'm going to do here is I'm actually going to split these all out into their individual terms. It's fine because everything's just being multiplied here. I know for fact what 5 times negative 3 is, so I'm going to go ahead and put those together, and I get negative 15. And then there's a couple different ways I can go about this next step. I can go ahead and make him happy, have a division, go from there. Or I can see this multiplication of like bases, a cubed times a to the negative 4th, and go ahead and go from there, which is actually what I'm going to do. So when I see like bases like this, that's really just going to end up being subtraction of the exponents. Actually, it's addition, but negative 4 is already negative, so it becomes like subtraction, I should say. Now notice 3 minus 4 gets us negative 1, so we go ahead and we do end up having to make a to the negative first happy, and we end up getting negative 15 over a as our solution here. Okay? Not too hard. They do take a little bit of thought and work to figure out what works best. I'm actually going to go ahead and skip over to 3 before we work on 2. So I know 4, there's nothing to simplify there, so I'm just going to bring him over, and then I'm going to split all of these out as well, and then pair them up with their like bases. Now a quick review, if there is not an exponent number shown, it's just a 1. So we go ahead, their split out is basically exactly what it was, but it's a little easier to see what we're doing here. I'm going to use my division rule, where you take a numerator exponent minus denominator exponent, and write them out. And then I need to simplify. I know that the 4 and the b to the 5th don't change, but anything to the 0 power actually ends up equaling 1. And anything to a negative power needs to flip to the opposite side. So this a to the negative 4th actually needs to go to the denominator to become a to the 4th. And then that 0, c to the 0 power equaling 1 does not change anything, so I'm just going to get rid of him. And I'm getting 4b to the 5th over a to the 4th. And then number 2 that we skipped, we need to use our product to a power rule. We have 3 products here. This means the power 2 needs to go in to all 3 of these terms. Now it kind of works differently for each one. Negative 4 squared times x minus 3 squared, and the x minus 3 is in parentheses, times parenthesis y to the 5th squared means that we also have to use our power to a power idea for the second two pieces. So -4 times -4 is easy enough. That's just 16. But then we get x minus 6 x to the -6 and y to the 10th power. We're pretty much done from here, other than the -6 is unhappy in the numerator, so we need to flip that exponent and its term into the denominator. So we end up getting 16y to the 10th over x to the 6th. And that is our solution there. Now, this next part, simplifying radicals, is a lot of review. I'm going to go through them, talking through some of them, but mostly just working through them. To start though, this review, 3 squared is just 3 times 3, which equals 9. So the square root of 9, just what times itself 2 times equals 9? Well, we know that's 3. Similarly, the cubed root of 3 is just 3 multiplied by itself 3 times. That's 27. So the number multiplied by itself 3 times, that equals 27. For the cubed root of 27 is also just 3. So we need to simplify. There was a couple different ways we did this last semester. We did our factor trees, where we found all the prime factors of something, in this case 2, 3, and 3. Wrote those out in our square root because these are actually equivalent to each other. Found pairs because we're trying to find square roots, and whatever came in a pair came outside. And we had 3 root 2 as our solution. Now, there's another way we could do it. We could have stopped here. We could have said, okay, these are square roots. I know the square root of 9 is a perfect square 3, and the root 2 just stayed. I almost prefer the factor tree better unless you already have all of the perfect squares, 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, so on, memorized, okay? And then you'd also have to have the cube roots memorized for 3 and beyond. All right, number 2, I'm just going to work through. You can follow along. I'm going to do the factor tree. So once I simplify it out and multiply by the 5 that was originally out front, I end up getting 20 root 2. Okay, so this next one, I am trying to find a cubed root. This is a little different than we've done before. Instead of trying to find pairs of 2, though, you're simply trying to find pairs of 3. So I need to find pairs of 3 for 250. Thankfully, that's not going to be too hard. There's a pair of 3 5s. So we bring that out front, so we have 2 times 5 cubed root 2. So 10 cubed root 2 is the simplification here. Okay? Similarly, we can find the cubed root of 189. This is 3. And let's see. 63. And 3. And 21. And 3 and 7. And we found all the way down to our primes. We do have a group of 3. If there's not a group of 3, you can't simplify the cubed root. So we end up getting 3 cubed root of 7 as our solution to that one. All right, this next one. It can be a little scary to have a negative inside of something that looks like a square root. Although this is actually not a square root, it is a cubed root, so having a negative inside is not a big deal at all. We just need to go ahead and find our group of 3, if there is one. So notice in this group of 3 we have a -1. That's just going to make the whole group negative. And we get -2 cubed root of 5 is our solution. And lastly, we have 6 cubed root of -160. This is similar to that last problem, where we are going to find the factors, the prime factors of 160. Lots of 2's here. So we have to find groups of 3. If there's more than one group of 3, well, we'll use it. There is not more than one group of 3, actually, so no need to worry about that. You take your group, bring it out front. Once again, that group is going to be -2 times 6 cubed root of 2 times 2 times 5, which is 20. Nothing else can be simplified in there, so we have -12 cubed root of 20 as our simplification. All right, that's all. Have a great night.